ready whenever.
I gotta wait for this person's okay first, so.
Gotcha.
If I can do the introduction first. I'm gonna need your mic.
Go for it.
So sorry, I know you're much taller down here. Just do that. Sorry, we're gonna have to change it. Hello again. For people who have heard me speak many times, our next speaker, I am gonna read the bio again. So give Hacker Tracker a second to pull up. Because Hacker Tracker decided to crap out immediately on me. Cool. All right, so our next speaker is Danielle McGuire. They have 8 years of experience in electric power cybersecurity and the security of industrial control systems more generally. When she's not doing that, she enjoys reading, cooking, and tinkering with electronics. Her main technical toolkit includes Python, Bash, C, microcontrollers, and SBCs. She is currently learning Rust, containerization, RISC-V, and radio. She would love to meet people and chat. Good icebreakers include, how can I get started with hacking EV chargers? And what is the relationship between cybernetic and surveillance capitalism? And the time is yours now.
Thank you.
Hello. Thank you, everyone. I'm really excited to be here. Thank you for that introduction. My name is Danielle McGuire. I have been working in ICS cybersecurity for almost a decade now. I am currently looking for work, if anyone knows anyone or is looking for an OT professional themselves. And we will not be talking about cybernetic capitalism or surveillance capitalism today, but hacking EV chargers. And we're going to look at doing this in a couple of different ways because these are vulnerable in a lot of different ways. But primarily, we're going to look at hacking individual models and then hacking the communication protocols themselves. So this is a very simplified diagram showing the EVSE ecosystem, the EVS ecosystem, because there is a complex interplay of actors, assets, and technologies here. We will look at a more detailed depiction of this later on, but what we have at this point is we have the car, the charger, the cloud management, and the utility. The charger we call EVSE, Electric Vehicle Supply Equipment. The charger or the cloud server we'll call the CSMS, the Charge Station Management System, and then the utility, it's like your electric company who you pay your electricity bill to. And critically, that's one of the things that I want to point out on this diagram right here. You can see that they are showing AC power flows, DC power flows, and communications flows. When we look later, we will see the communication flows in more detail. But at this point, I just want to note that no communication occurs between the utility and the car itself. And although it does have some communication shown between the utility and the EVSE, this is not the control traffic for the EVSE. This is the utility talking to the building management system, if there is one. The utility has no ability to monitor or control this EVSE in a typical deployment. Every utility in North America is different. Mine owns no generation assets and also no EVSE for like customers, like the general public. We have a couple on our corporate campuses, but the utility is not the person that is responsible for securing this equipment. That is the responsibility of the individual owner-operator. In Pittsburgh, our top 3 customers who have EV chargers are EV dealerships, bougie apartment buildings, you know, that one apartment style that goes up in every city made of corrugated steel, and the parking garage by Google Pittsburgh. So it's not something that the utility can do. It's not something that, to my knowledge, any centralized organization is able to do, but it's going to be a decentralized and cooperative effort. And this is really important because EVSE is a growth industry. Some of you might know that we are in the midst of a climate crisis that might kill us all. And a lot of smart people are working on this problem. And one of the major challenges that they are running into, I want to show you this, is that EVSE significantly is increasing the load on the grid. As it exists today, if we put every single EV charger in a botnet and then turned them all on at once or turned them all off at once, because either is sufficient to destabilize the very precise balance between generation and consumption of electricity that is necessary to keep the electric grid stable. If we were to turn all of our chargers on or off as they exist on the grid today, there is not enough load to significantly destabilize the grid. That is not a threat vector or a threat scenario that we are too concerned about right now, but this might change because pretty much everything that you have probably seen in the wild is a level 2 DC charger. There is DC fast charging that is available for consumers now. I have spoken with folks who own it, but the kind of things that we are going to be looking at today, and specifically when we look at what has already been done, the research at Pwn to Own, it is level 2 chargers, but the Tesla supercharger and extreme fast chargers are both orders of magnitude they consume orders of magnitude more energy. Real fast, for folks that maybe don't think about electricity all day, electricity is the flow of electrons. The push that those electrons receiving is the voltage. The rate at which those electrons are flowing is the current. And when you multiply the voltage by the current, you get electric power in watts or kilowatts or whatever. And then when you multiply the power by the time, you get the energy. So kilowatt hour is a measure of how much energy something is going to use, and its wattage is how much energy it uses over time. It's joules per second. So what we are seeing here is that these extreme fast chargers are consuming 50 times as much energy, or they're consuming energy at a rate that is 50 times greater than these level 2 chargers. And then when we compare these with other household appliances, and I'm sorry, I know this is really hard to see, but the level 2 here, if you can see, is 7.2 kilowatts. And yeah, the air conditioning for a room is, I think, 1 kilowatt typically. And we have the central air here is 2 to 5 kilowatts. We have the well pump, 1/3 to 1 horsepower well pump gets up to 1.2 kilowatts. So when we're talking about level 2 chargers, those are still on the same order of magnitude as the traditional household appliances, but the extreme fast chargers are going to be orders of magnitude more powerful, literally. And this is an example level 2 charger that we're going to look at today. And I will make these slides available afterwards. Also feel free to take pictures of them. But the, I'm going to, oh, I would like that. Thank you. Thank you. Yes. All right. This is a level 2 charger with max 12 kilowatts, but typically 7.2. As of last fall, you could have it for $550. And the things that I want to point out on here, it has Wi-Fi, it has Bluetooth, although I don't think I put that there. It has 90 days of charge data locally. It does its firmware updates just right over Wi-Fi, or on some models over Bluetooth even. And we will look some more at these internals, but specifically it's using an ARM9 processor on its main control board. It's using some RAM and some flash, and it's also got a secondary, it's got a Bluetooth model, and it's got a secondary MSP430 chip on its metrology board, and this will be important in a second. So who here has ever done any hardware hacking before? 2 people, 2.5. All right, 2.5-ish. Well, that's okay. So the deal with hardware hacking is pretty much try to get the firmware. If you can get the firmware and analyze the image, then typically a lot of the skills you're going to use are your traditional memory corruption, vulnerability research, or just privilege escalation on a Linux box, because these things are almost always Linux boxes. So much worse than when they're Windows boxes. But on this board here, you can actually tell a lot about it just by looking at it. And by the way, all of these internals that we're getting are from ZDI, from the Pwn to Own automotive competition in Tokyo. We will be discussing that more in a bit, but they were good enough to put pictures of all of the things online. So it's not just this ChargePoint charger. Don't mention this outside this room. Well, the reason that we're talking about ChargePoint is that I happen to know that ChargePoint is what is deployed all over the city of Pittsburgh right now. There are different models, and this was the ChargePoint model that was in the Pwn to Own competition. Great, thank you. But when we're looking at this, you see that there are a few chips on the front of this control board. You see that there are, do I have not a cursor, I guess. Generally, the bigger the chip, the more complex it is. You got to shove more transistors into there. You also notice the pins that are coming out of these. Those two right there, you can see the pins, they're visible. This one right here, it's got its pins underneath, guaranteed. It's probably got about 64 of them. I could have looked that up, but I chose not to. But yeah, there are a couple things there, and then everything else on there is passive component. Resistors or capacitors, or in some cases inductors, also diodes and transistors. And the important things about these is that these just respond to the electricity signals that they receive. There is no intelligence in them. They're dumb devices, basically, so there's not really anything for you to hack unless you're going to try and hack by giving it too much voltage. But let's look at the metrology board, because that one a second ago was the control board. It has very small components because it is handling 3.3 volt or 5 volt circuits. This has much larger components because it is actually measuring the electricity that is charging the car. Now we're talking tens of volts, even hundreds of volts. There's components in there to rectify the power and smooth the power and make sure that the power doesn't exceed any points that could damage the equipment. And you notice that all of this equipment is much bigger because it has to be. It has to be physically larger in order to handle the more powerful electricity that's going through it. So just quick show of hands, who thinks that we are more likely to find a vulnerability here in this control board with its 4 integrated circuits? All right, one person, thank you. Who thinks we're more likely to find it on this metrology board that has 1 IC and a bunch of inductors and stuff? Couple more people. You are correct. If anyone here has ever watched a series of YouTube videos called, I think, Make Me Hack, but Valerio Di Gianpietro, who wants to be your friendly Italian hacker neighbor, has put out an excellent series of videos on hardware hacking for absolute beginners. He will take you through the entire process of not even having a device, but doing open source intel on like the FCC database, or there are wikis of people that have already done a lot of work on a lot of devices and have shared their information. But one thing that he always stresses is take the easiest path first, because there are a lot of ways for things to go wrong. If you are hitting roadblocks on a particular vector, it is possible and likely that there are other vectors available that don't have those roadblocks because the creators of the device simply did not put them there. So he always says, if you hit a roadblock, try something else. And so that's what I'm here to say. There is a lot more protection on the control board because obviously it's a control board. No one bothered to do anything with the MSP 430 on the metrology board. And before we start to dig into the CPH50 consumer charge point a little bit more, I just want to say that this is not just this vendor. I'm picking on this vendor because I see them a lot, but all EVSE is vulnerable. I said that there were Pwn-to-Own competitions in Tokyo, Pwn-to-Own Automotive, that in 2024 and 2025 offered EV chargers as a target, EVSE. And what they found is, I believe last year in 2024, every single device was ultimately owned, RCE'd, I believe. And this year, we don't have all of the results yet. We are going to get those results almost certainly during Hacker Summer Camp when people release their findings during DEF CON and Black Hat. But This year, what we do know is that there were 39 zero days that were discovered, hundreds of thousands of dollars in prizes given out. There were 2 specifically in the Tesla wall charger. I believe 4 teams hacked Tesla with 2 unique O days, and we'll talk about Tesla in the next slide. But one thing that I also want to stress is that as it exists today, there is not enough of this on the grid to destabilize the grid if they are all turned on or off at once. But this may well change over the next 10, 20 years, especially with a lot of the other changes that are necessary for the electric grid to get through the climate crisis. And I'm just going to get this out of the way now. Well, we'll talk about that in a second because I already built you up for this. We need to talk about Elon. I mean, yeah, he is a laughable man. He is a sad, pathetic little man, but he's also a Nazi. And he has a lot of power right now. And he is a major EVSE manufacturer. So I showed you, one thing I didn't show you, I guess, but at Pwn to Own, they have maybe 7 or 8 different vendors of EVSE. And part of this is because the Biden administration, as part of its Infrastructure Recovery Act, put billions of dollars into trying to build an alternate EV charging infrastructure in the United States to Tesla's. Tesla uses a proprietary charging point that they license out to the auto manufacturers. It's the exact same strategy that Apple uses to get you to buy proprietary Apple products. Well, I cannot predict the future. But as long as Elon Musk has the power that he has in the federal government, I think it's fairly safe to say that we are not going to have an alternative EVSE infrastructure. I think that there is still going to be a focus on modernizing and expanding grid capabilities, because I think that no matter what political party you're on, people recognize that the things we want to do with the electric grid in the 21st century, the grid is not ready for. It's pretty much the same design that we've had for over 100 years. It's people sitting in a control center somewhere, sending power from generation sources down to customers, following very deterministic schedules. But the grid of the future is going to have people sending power back up to the grid from solar or wind. It is non-deterministic because solar and wind are variable generation as opposed to the kind of known generation that you would get from burning coal or natural gas, but also nuclear. And there's a lot, but I think that it's safe to say that at this point, the American auto industry is expecting to just license the proprietary Tesla charger. So we will see where everything goes. I think that it is safe to say that probably the importance of pen testing individual EVSE hardware models may not be as important, but the broader thing of we are putting a lot more assets onto the grid is not going to go away. And also, this is why I pointed out that Tesla had 2 0 days discovered at Pwn to Own Automotive in January, just to show that, like I said, there is not one vendor that does EVSE charger security better than the others at this point that I have seen. Tesla is just as vulnerable as your charge points or your juice boxes or your Autels or what have you. But back to the CPH50. They got root on this thing in 30 minutes. They talked about it. They said that it took actually way longer for them to get the charger than to get root. And not only did they get root in 30 minutes, it was a remote code execution, no authentication over Bluetooth. It was command injection in the password field. Command injection in the password field. I was reading the write-up beforehand to make sure I was remembering that right. And yeah, they don't want to store plain text passwords, so they pass your password to a Linux command that's supposed to encrypt it. Something in the OpenSSL suite, I think, but it's just a like %s inside something that they pass to system. It's bad. But we also can use this to understand a little bit about how hardware hacking works, because once you get to the actual digital communications, it's pretty much the same as any other memory corruption vulnerability research. But how do we get to that point? And Computest Sector 7 credited some Kaspersky research here that showed that this CPH50, like pretty much all embedded devices, it is a Linux device, and it runs U-boot, and it has a JTAG interface. And this is also something that Valerio Di Gianpietro has gone into a lot of information on. Finding your hardware debug interfaces. There are a couple of them. There's, I should not have said that when I don't have any others off the top of my head and none on the board, but there's JTAG and there's other ones, but most people use JTAG, and it's just a few pins. There's like a UART, thank you. Thank you. It has pins. It has a receive pin and a transmit pin and a voltage set pin and a ground pin. And it's really just a serial communication. You can use a standard USB to serial converter. In fact, I think that is what you use, unless you have a JTAGulator, which is a dedicated hardware device for automatically determining the details of your port. You find these hardware debug ports by looking for sets of exposed pins on the circuit board. Once you find them, you can use a multimeter to determine which pins are static high voltage, static ground voltage, and fluctuating voltage. And then try a few different pin connections until you find one that gets you the information that you need. So that's how you talk to these things over the JTAG interface, which almost all devices are going to have at least one. Although one thing that a manufacturer might do is they will have the JTAG interface somehow disabled on their production devices. So you might have to find a way, and sending it an enable is almost always like sending an electric signal to the right place. But once you have the JTAG, this thing was set to use auto boot to just boot up into the binary that they wanted. They didn't want to do that. They wanted to explore the Linux file system and operating system. So they described how Kaspersky, I think, downloaded the binary image and then patched the image, patched the password validation functionality so that it would allow Kaspersky to use their password. But the Computest Sector 7 guys said that sounds way too hard. We want to do the easiest path first. So they just booted into single user mode. And then they added their own user. And then they started poking around and they found out that, yeah, Telnet is just listening on the local network and it's got a set UID shell. So, sorry, this is different than the password injection one. They have so many vulnerabilities and they write them up. But what I'm trying to say here is that the vulnerabilities themselves are straightforward. The hardware hacking process is also straightforward. And if folks are looking for CVEs, these are still very juicy targets. They may not be as critical because EVSC is in flux right now, but there is a lot of other critical grid technology that this same principles apply to, be it DERs, smart inverters, battery energy storage systems, vehicle to grid. I don't know if I said AMI, advanced metering infrastructure, or smart meters, but there's a lot of tech to research and a lot of vulnerabilities to find. And here are some further links. Again, I will share these slides afterwards. Okay, so yeah, looks like we're about halfway through, and that's good because now let's go back and let's talk about the EVSE ecosystem in greater detail. I showed you earlier that we have the CSMS in the cloud, your charge station management system. You have your EVSE, your electric vehicle supply equipment. You have your car, and you have your utility. So in this model right here, this and this, the EVSE network operator and the grid services aggregator up there, are both major components of what might be considered a CSMS on the other diagram. Right here, we see the EVSE. We don't actually see the car itself on the diagram. We also have the building management system right down there, which I mentioned. This is what handles like the lights and the air conditioning for this hotel. It's a very, very under-inspected attack surface. Has anyone here ever pen tested a building management system? Wow. Okay, that's why you're keynote. Uh, that too. But yeah, very underexposed. And then you've got the utility over there on the far right. And it's a little hard to see, I apologize, but all of these red connections here are IEEE 2030.5 or OpenADR 2.0. And these are automated demand response protocols. One of the ways that we are handling the fact that wind and solar are non-deterministic and variable is having a protocol that can turn on demand assets on and off dynamically for the exact balancing of the generation of power versus the consumption of power. So that is how automated demand response is meant to work. It is still very much in progress, but that's what these communication between the utility and the building management system are. It is not the utility sending OCPP, the Open Charge Point Protocol, which we will discuss more in just a second, but it is sending these open ADR signals that are designed to build a interdependent, decentralized, geographically and organizationally dispersed network that is capable of dynamically retaining stability by sending communication back and forth about what is needed and who is doing what. It's really fascinating stuff. Come find me if you want to talk about it, but it's not the Open Charge Point Protocol. The Open Charge Point Protocol is what is used by the CSMS in the cloud to manage the EVSE. It is pretty much everything I've seen in the wild uses OCPP 1.6 without the security extensions. There is an OCPP 2.0 and an OCPP 1.6J that bring the security extensions from OCPP 2.0 back down to OCPP 1.6. And the major one here is that none of this traffic is encrypted by default. This is all plain text. This is all right over the wire. If anyone here has ever man-in-the-middled something, the attack that I'm about to show you is not going to be very novel at all. But the critical thing here is OCPP 1.6 has some commands to start and stop transactions, to ask the cloud whether or not somebody is authorized to use the server or to use the charger, and also to update firmware. Both do I need a firmware update and give me the firmware update. So someone that is listening on the local network and has the ability to respond to things faster than the legitimate charge management server can basically do whatever they want. Let's look at that. So we're going to walk through this man-in-the-middle attack, and for those of you who have done a lot of man-in-the-middle, I apologize. It's not going to be very interesting. I'm also almost certainly going to make some technical mistake. Please be nice to me. But what happens is that when the management software tells the OCPP client inside your charger that it is time to do a firmware update, then that client goes ahead and sends the request for firmware over to your legitimate charging service in the far right. But if you are sitting on the same network, then, and in this situation, they just use the tools EtherCap and man-in-the-middle proxy. We'll talk about some other tools in a minute, but then just, intercept the firmware update. Tell the EVSE, yeah, I've got firmware for you. It's at this IP and it's named this. So in case you can't see, I don't think anyone can see, the red IP is different than that IP. The firmware name is different than that firmware name. But then when it goes to download it, again from the same adversary, in this case, the adversary is passing back a Java binary that has the log4shell vulnerability inside it. Just because, anyone here remember log4shell? Anyone get enough sleep? 2 weeks of no sleep. That's right. And as we showed on the previous slide with the pwn-to-own vulnerabilities, there are ample vulnerabilities in all of these. So it is not at all. It raises the bar to demand that the attacker bring a 0-day or an end day in whatever charger they're attacking, but it is not a particularly high bar. And then at that point, it's just pretty much game over. And it was game over ever since the attacker was able to tell the EVSC where to get its firmware update from. And yeah, that's pretty much all it takes. So simple that a Muppet can do it. So then let's talk about the tool that I made, and then I see that we are going a little bit faster than I had anticipated. We can either do more questions, or I can go into greater detail on anything that we talked about, but I think we probably got about maybe 10 minutes of content left, and then we'll figure out what we want to do. But yeah, EVSE tool. I would like it to be the Swiss Army knife for EVSE pen testing. I am very busy and very tired, but I am doing the best that I can. And what the tool is capable of doing today is on a local area network. So we're talking if you are wired or if you're running a container simulation, it will just read your plain text OCPP 1.6 traffic in real time. And then on the Wi-Fi LAN, I am currently capturing the initialization vectors to decrypt that, but I haven't figured out how to get my Python script to decrypt Wi-Fi in real time once I have the initialization vectors. So that is what I am working on. But the goal here is that this will be a very straightforward turnkey pen testing solution where someone rolls up on a network where they find that EVSE is deployed. They get onto a Wi-Fi network by whatever means are appropriate. And then from there, they start a sniffer at the command line that will then show them in real time OCPP traffic as it goes across the wire. And so the major things that you're then looking for here are the start and stop transaction pair, authorization requests, and the update firmware stuff, although that is probably not going to be a common traffic. Because once you have those, just simply by virtue of sending start transactions or stop transactions, you are able to in some cases, start and stop the transactions. In other cases, it will be set up so that the person who wants to use the EVSE has to get approval from the cloud. In that case, it really is as straightforward as make sure that you have your response to the charger before the legitimate service can get it to them, because there's no other validation in this protocol outside a simple you might need to capture a particular identification token so that you can say that you are who you say that you are, but that's the sort of thing that you get just by sniffing it for a little bit. So what I would like to ask is that if anyone does use this tool to try and hack some EVSE, or if you break my tool in any case, please let me know and share the data, share the use case. Let me know where I have done poorly so that I can do better. And we can make this together the best utility for this case that we can. Because, yes, I want this to be something that a script kiddie can use so that then all of us can go to the owner-operator of the EVSE and say, yes, this is a tool that a script kiddie can use. You should upgrade to OCPP 2.0 or OCPP 1.6J, which includes encrypted communications, which just breaks this tool. Simple as that. I think that OCPP 1.6 should be considered as secure as electronic codebook, ECB, for encryption, or WEP for Wi-Fi, which is just to say it's not. And so I have a screenshot of the tool here. Let me see if I can zoom in on this at all. No. Maybe. Think. One moment, please. You know what? Sorry, one moment. I know where to get us a better picture of this. Um, so yes. All right. Can folks see that okay? Great. Great. Thank you. So let's scroll all the way up to the top. So what I have here is we are using Docker containers to run this tool in two modes. This mode right here is just, it is acting in sniff mode. So it is listening as a sniffer. And over here, this is emulating the CSMS. And I don't have, or no, I'm sorry, this is not emulating the CSMS. This is emulating the act of querying the CSMS. So over here, we're going to see the traffic that the CSMS sees. And you see that first, it's just going to connect to a WebSocket with a particular URL. This CP1 is a unique identifier for the particular charger. And it sends back an HTTP 1.101, which I'm pretty sure is just saying we need to change to the WebSocket thing particularly. Is there? No, yeah. Okay, so then over here we can see the particular messages that the simulated EVSE, the simulated charger, is using. And so the first thing that it's going to do is it's just going to send a boot notification to the server in the cloud. It says here that its model is changed, meaning its vendor is to-do. And we receive that over here. So I think then next it asks to authorize. Yes, it sends the boot notification. And then here it goes ahead and says, I would like to authorize, or I would like to ask if so-and-so is authorized to use this. So the ID that I sent it was just 012345667 backup because it's a 20-character thing. And over here, you can choose to have your tool respond to any authorized messages, any start or stop transactions with whatever you want. In this case, I just chose to have it reject any particular authorized stuff, but then just show you how the start and stop work as though they were authorized. So we have the authorized message come in right here. I think that these are duplicated. I forget why we are having all of these duplicated, and I apologize for that. But you see here that it sends back an immediate status equaled blocked response, which is then received over here by the simulated EVSE. And just by the way, if you go into Wireshark today, Wireshark is capable of decoding the underlying WebSockets connection. It is not then capable of decoding the OCPP layer on top of that. Meanwhile, SCAPY, SCAPY, the main Python protocol dissector, it does not have stuff for either OCPP or WebSockets or OCPP. I implemented both of those layers, and it also does not have the decode Wi-Fi in real-time layer, so I'm working on that. But that is the status if you were to go and try and look for other tools. You can read this OCPP traffic in Wireshark. As you can see, it's fairly human readable. It's just JSON structures being passed back and forth over WebSockets. But to the best of my knowledge, and that is also one of the projects that I am attempting to get done here, is get the rest of the standard blue team, red team forensic suite updated with these and the other key protocols. But then you notice here we're going to try and do three things. We have a start transaction, which gets denied, a status notification that is sent back, and then a stop transaction that gets denied. And then when it receives the start and stop transaction over here, it is pretty much up to the charge system management system to decide what it wants to do with it. There is no further, the only information that is passed back and forth is that on the authorize, we send an ID tag that is meant to identify, like when you're out driving and if you have an account with ChargePoint or any of these people with Tesla, you get a little 20 number numeric ID that identifies you uniquely. And this is every time you want to charge your car, you're going to send that, or you're going to tap something on the charger and it's going to read your ID and it's going to send it up to the cloud, and the cloud decides whether or not that is authorized. The people that the Computest Sector 7 people that wrote up that CPH 50 breakdown earlier also describe how they went poking around the ChargePoint cloud servers for CSMS, and they found a lot of other stuff there. I do not have any authorization nor particular expertise in pen testing web applications, but really great stuff. Definitely recommend checking it out. But then further down, when we tried to do our start transaction, oh, I just made that small again. When we try to do our start transaction, the only thing that we're going to send on over is, start transaction, and I made it small. Where is the... There we go. Start transaction, connector ID. You see the 0 up to 9 up to 9. That is the same ID that we previously failed to authorize in the authorize step. So that's why the tool then does not allow the start transaction or any of the subsequent things. But that's all it is. It's an ID tag, and all of the validation is done in the cloud. So if you, as the malicious actor, want to send a message saying, oh yeah, that ID tag is fine with me, there is nothing else that the system will check. So thank you for bearing with me there. I think the last thing that I wanted to make sure to hit on right here what can you do if you own EVSE? One of the good news is security hygiene goes a long way. Just making an inventory that has all of the EVSE model number and firmware version, all of the network gear that it uses, all of the network diagrams that are relevant, all authorized users, and all user accounts that may be using it in general, authorized and unauthorized. For all accounts, put them in some kind of credential management solution. Enforce a decent password policy. Make sure people don't reuse passwords. Change it if there are breaches. Make sure that procedures to update the password are in place and executed regularly. I mean, patch your stuff. You can do N-2 versioning or like a delay of a couple weeks on versioning, but don't let critical security updates sit out there for months and years. And I think the biggest one, don't put this on guest Wi-Fi. I hope that I have shown that this thing on a local network doesn't have any suspicion. It doesn't have any fear. It assumes that if you can talk to it, you are a friend, which is par for the course for a lot of these things. But just putting it on a dedicated subnet with a like WPA3 and a strong password, even a pre-shared key, having strong user accounts, changing the default credentials. I forgot to mention, but in 2024, one of the vulnerabilities that ChargePoint removed the day before the competition was a vendor backdoor in every single ChargePoint product. Change your passwords. Change your encryption data. That's also not handled well. But I also have like some stuff for the C-suite. NIST 8473 has, or is that? Yeah, NIST 8473 is a NIST document on creating an EVSE security program. They map to the NIST cybersecurity framework. It's very boring and probably pretty effective. We don't have to talk about that, but we can if anyone wants to. Thank you so much. Any questions? Yes.
So for those, because only two of us raised our hands for hardware hacking, what are some of your favorite beginner tools that people in this room can go get so they can go do this?
Yes, thank you. That's great. First up, multimeter. If you've ever used these in a high school physics class, a good one is like 20 bucks. You need one that can do DC and AC voltage, like pretty much not a toy. It'll be able to do that. If you can get an oscilloscope or a logic analyzer, that is great. But I would think that the two biggest things are a bus pirate that is capable of handling a lot of different serial USB interfaces. And then, I'm sorry, I'm completely blanking. There was a bus pirate, and then there was a different one. Oh yeah, just a USB to serial converter. And I mean, if you'll all indulge me for a second, I can pull up something from my blog that might have a bit more information. Does anyone else have any other questions?
No, we want to see your blog. That's what she said.
Yes. It's cybernetic philosophy and computers.
Oh, yes, I'm warned.
Yes.
Craft.
Well, thank you. So let's look at this, because in this case, what I was trying to do is I wrote a custom Rust kernel using a wonderful tutorial on GitHub, and then we had to flash it, in this case, just to the Raspberry Pi. So you see over here, my friend loaned me this FT232, which I think is Yes, it's a USB TTL transistor something logic, but just it sends USB into 3.3 to 5 volt signals, and this thing was just like 10 bucks. So that was ultimately, I think we did UART. Yes, it was a UART, and then here I can even just show you what it looks like. Where is cursor? So here we're just resetting it and plugging it back in. And then you get the data. So you see that what we've got down here, as I play this again, we have a regular cable going to, and by regular I mean a micro USB going to the Raspberry Pi, which then has some wires connected to the serial converter, which then send the that's a power cable. There's no data being sent over that. That's just it. That micro USB is just for power. The computer is plugged into one end of the 232 USB to serial converter, and then those wires go directly to the board. So that is actually how we flashed the firmware on there over UART. So when we looked at JTAG earlier, if you wanted to directly flash firmware onto a device, often it's possible to do that through JTAG. But it might be locked down, and also it's just not the easiest path. Take the easiest path first. Yeah, thanks. Great question. Yes?
So you spoke a lot about network connectivity to the network via the converter. Is there any way to get from the EV connector to the vehicle? Are you getting any vehicle data?
Yes, thank you. That's a great question. So what I have found is that there are computers inside your converter or computers inside modern cars that are capable of making web requests. So what I have found is that it is possible to have your EV charger tell the car charger to reach out to a particular domain somewhere and do something. I have not pinpointed this exact mechanism, and I have not found anybody then who has taken the next step of using this to actually, through the EV, hack the car directly. I'm asking everyone about it, so thank you for bringing that up. But to the best of my knowledge, the car charger can tell the car to reach out to somewhere, but I haven't found the exact mechanism.
Talk to me later.
Thank you. Anyone else? All right. Well, thank you so much, Rochester. This was wonderful. Yeah. Thank you.